In this class, I will discuss about a thick cylinder problem, which you have learnt in your strength of materials as Lami's equations. Since in SOM, the same topic has been discussed in the Lami's equation. So, in the case of a thick cylinder, what happens is, whenever it is subjected to an internal pressure or external pressure, here PA is the internal pressure, PO is the external pressure, stresses will develop in two directions. So, stresses will develop in radial direction. So, if O is the center of the cylinder, so stresses will develop in this radial direction. These stresses are denoted by sigma r, and also in the circumferential direction, sigma theta. So that means polar coordinates are used to solve problems of thick cylinders. So the stresses which are going to develop in the radial direction are called as radial stresses, sigma r, and the stresses which are developed in the tangential direction or circumferential direction, it is called as circumferential or hoop stress. So here let me take this A as the inner radius, here to here, and B is the outer radius. When such problems are given, the question will be to find the stress distribution in the radial direction as well as in the circumferential direction. So this is the cross section of the cylinder, which is subjected to both internal and external pressure. This is the longitudinal section. So length of the cylinder is taken in this direction, x direction. So it is subjected to internal pressure PA and external pressure PO like this. In problems of thick cylinders, normally you will be having two boundary conditions. The first boundary condition is at R is equal to A. That means at R is equal to A means at this point, at this circumference. So at this edge here, you will be having the pressure as PI. And the second boundary condition is at R is equal to B, that is the outer edge here, the pressure will be PO. If both internal and external pressures exist on the cylinder, these two are the boundary conditions. Suppose if there is no internal pressure, only external pressure exists, then internal pressure is taken as 0, PA is taken as 0. Or in other words, if only internal pressure exists, there is no external pressure, then P naught or PO will be taken as 0, only internal pressure value you have to take. So here the units will be, normally this A will be in millimeters, B will be in millimeters, radii in millimeters. This inner pressure and external pressure, they will be Newton per meter square MPa. Stress values also we are going to get in MPa. Please note that both pressure and stress they will be having the same units, Newton per meter square. Now these stresses are found out using these two equations. These two equations can be derived by applying the boundary conditions of the fundamental equation. So here, after doing all those things, we are going to get sigma r expression, that is the expression for radial stress as A square Pi minus B square PO divided by B square minus A square minus of Pi minus PO A square B square by B square minus A square into R square. And for radial, for circumferential stress or hoop stress, same expressions and terms will be there, but with a positive sign. If you observe this, one thing you can see that the first term of course is a constant, whereas the second term it is constant divided by R square. The meaning of that is the variation of the sigma r with respect to R. So sigma r with respect to R, the variation is a curve. So if you plot the variation of sigma theta and sigma r in two cases, suppose if you are taking only internal pressure is existing, that means your external pressure is 0. In that case, the variation will be like this. So I have shown the sketch on either side. So this sketch, this curve represents the variation of sigma theta from R is equal to, this is the origin, Here r is equal to a, here r is equal to b. From r is equal to a to r is equal to b, this is how it reduces. Sigma theta reduces. So the variation is occurred. Similarly, if only internal pressure is there, the pressure here at r is equal to a will be P only, and at r is equal to b there is no pressure. Therefore, at r is equal to b, our sigma r value will be 0. And here, suppose if only external pressure is there, then P0 will be equal to taken as P and Pi is taken as 0. Here the variation is like this. Sigma theta decreases from r is equal to a to b, and here sigma increases from r is equal to a to b. So this is how, anyway, in both the cases it is a curve. So variation of sigma and sigma theta with respect to r is a curve. So this is how we can plot the stress distribution across the thickness of the cylinder. So you might have studied this in strength of materials also. So only thing is here, by knowing the boundary conditions, we can get the constant. So if you observe here, this first equation can be written as sigma, can be written as, if you take this as a constant a minus b, another constant. This entire thing is a constant divided by r square. So this is the equation, and sigma theta can be written as a plus b by r square. So this is how the equations of radial stress and tangent stress can be written in the case of a thick cylinder. So these two equations are called as the Lami's equations. So these two equations are called as Lami's equations. A and B are called as Lami's constants. Now I will take up a numerical example wherein how to find these stresses. So in this example, so he has given the values of inner radius. So that is inner radius A is 100 mm, B is 150 mm, external radius. Internal pressure Pi, internal pressure Pi, he has given 12 MPa or 12 Newton per mm square. There is no external pressure, so that is 0. So now the question here is, we have to find out sigma r at r is equal to a and r is equal to b, that is at the inner and outer edges. Sigma theta at same points at r is equal to a, r is equal to b. So this is how the problem is given. Now in this case, since he has given there is no external pressure, we have to take P0 is equal to 0 in these two equations. Now directly you can substitute these values. So what I will do here is, first I will calculate at r is equal to a means at the inner edge or inner circumference. At the inner circumference of the cylinder, that means at r is equal to a. So what is the value of sigma r and sigma theta? So let me calculate sigma r. So what we have to do here is, we have to put r is equal to a in this expression. If we put r is equal to a, and also we have to take P0 is equal to 0. A as 100 and Pi as 12 Newton per mm square. So now here a square is 100 square into Pi is 12 Newton per mm square. Please note that the unit should be newtons and millimeters. So that is the first value. This value becomes 0 because P0 is 0. Divided by b square minus a square, that is divided by b square is 150 square minus a square is 100 square. So this is the first term minus second term is this Pi minus Po. Pi is 12 minus of course Po is 0 into a square b square. So that means into a square, that is 100 square into b square 150 square divided by b square minus a square into r square. So b square, that is 150 square minus a square 100 square into r is equal to a. I have to take a is nothing but 100 here, square of that. So this is the value of sigma r. If you simplify that, you are going to get sigma r value as minus 12 MPa, negative. So sigma r is negative, minus 12 MPa or Newton per mm square. So this is the value of sigma r at the inner face. Inner face is this here. So this value, because only internal pressure is there. So this is the diagram. So this value now it becomes how much? Minus 12. So it is minus 12. So here I have shown this diagram below the horizontal line, but its value is negative. So minus 12 you have got. Next sigma theta, look at sigma theta in this equation. So circumferential stress or hoop stress is given by substituting that value of r is equal to a is 100 here in the second equation, 100. So second equation, if you substitute, what happens? Everything remains same. Only thing is instead of minus, you have plus sign here. If you substitute and simplify, you will get 31.2 MPa, positive 31.2 MPa. So this is the value, Newton per meter square. So you can see that this is positive. So this value. So this value now. So positive means I have taken above the line. This is negative. So here this value is how much? 31.2. 31.2 MPa. It is positive. Similarly, he has asked the value. Suppose if you ask the value at the outer circumference, that is r is equal to b. In both the expressions, instead of 100, you have to substitute 150, and you have to calculate the value. So now what I do here is, suppose if I want the value of sigma r and sigma theta at r is equal to b at the outer edge, this edge, at the outer edge. So at r is equal to b, that is 150 mm. That is, I can take outer edge, the outer circumference. So put r is equal to 150 in that. So I will get sigma r as, that is the radial stress as a square into pi. So all those things remain same. 100 square into pi. Pi is 12 MPa minus b square into 0. So that term p naught will not be there. Divide b square minus a square. 150 square minus 100 square. This is the first term. Minus pi minus p naught, that is 12 minus 0 into a square b square, that is 100 square into 150 square, divided by b square minus a square, 150 square minus 100 square into r square. R square is 150 here. So this is the substitution, and if you simplify this, you are going to get sigma r as 0. Please check that, 0. That means there is no radial stress at the outer edge, so this point. So here you can see it is 0, whereas here it is minus 1. That means this stress sigma r varies from minus 1 to 0. That is the meaning. So similarly, sigma theta will be equal to same two terms with positive sign. If you substitute and simplify, you will get 19.2 MPa. 19.2 MPa. So the value of sigma theta at the outer circumference is this value. So this value is 19.2 MPa. So it varies from 31.2 MPa to 19.2 MPa, whereas sigma varies from minus 1 to 0. So that is the meaning, and the variation is curve. It's a curve because this, you can see this equation, sigma varies inversely as r square, sigma theta also varies inversely as r square. So therefore it is a curve. So this is how we can plot the stress distribution in the case of a 6-cylinder subjected to only internal pressure. So suppose if they ask you to find by giving both internal and external pressures, then you have to substitute the values of both P and P naught here, and then so normally the inner edge and the outer edge two values will be asked. Suppose if they ask you to plot the stress distribution, then you have to go on give the values. For example, here like this. So here R varies from 100 to 150 mm. So what you can do here is, if you want to know the stress variation across the thickness, something like this. Suppose if you want to know, so here we have calculated only two values. One is 31.2, another is 19.2. So this is at 100 mm, this is at 150 mm. We can always find the values at R is equal to different values: 110 mm, 120 mm, 130 mm, 140 mm like that. So we will be getting different values here. So different values which vary from 31.2 to 19 point. So this is 110, 120, 130, 140, 150 like that. We will be getting different values of sigma theta here. Of course, this has come for sigma theta. Then if we join all these points by a smooth curve like this, that gives the variation of sigma theta from the inner circumference to outer circumference. Similarly, you can always find for sigma r also. In this case, sigma r is like this, so it is like this. So here we have got the value 12, that is minus 12. So similarly, you can find out the value. This is at r is equal to 100, this is at r is equal to 150. You can find out the 110, 120, 130, 140 like that. So if you get the values of sigma r by putting r is equal to 110, 120, 130 like that, you can join all these points by a curve. Then this gives the plot of sigma r, which is negative, whereas here it is 1. So like this, different points on the section. So you can find out the values of both sigma r and sigma theta. Sigma r actually it acts in the radial direction. Sigma theta is perpendicular to that, which acts in the circumferential or tangential direction. So this is how we had to analyze the problem of thick cylinder subjected to internal, external pressures or any one of them.